What's up, Precal? I know I'm not totally with the times here. You're not currently doing limits and asymptotes and things, but I'm told that it's coming back, and so it would be a smart move to go ahead and talk about this. And also, I think there's some clarification that needs to happen there. So, a couple of preliminary clarifications. First one being x minus, this is an example. I mean, it's not specific to x minus 2 over x minus 2, but not always equal to 1. Almost always equal to 1, because, let's say x equals 3, right? If x equals 3, then obviously 3 minus 2 over 3 minus 2, clearly that's 1. X equals 10 billion and 2, then, you get 10 billion over 10 billion, you get 1. There's one single x value that's going to cause you a problem here, and this is why it's not equal to 1 in general. What if I have x equals 2? That's 0 over 0. 0 divided by 0 is undefined, which means that although for every other value of x, this x minus 2 over x minus 2 is just going to be 1, and you have no problems, for x equals 2, you're going to get undefined. So in effect, if I were to graph that, you'd get y equals 1, except at x equals 2, you'd have a hole because that's the only value that doesn't work, is x equals 2. All right, the second one is 0.9 repeating equals 1. How do we know that one number is different from another number? That sounds like such a silly question. How do we know that two numbers are not the same one? Well, if I were to draw the number line, the real number line here, and here's 1, how do I know that this is not 1? Well, clearly, it's not at the same spot as 1. There's some space between those two. Well, what happens if I have 0.9 repeating? 0.9 is pretty close to 1. 0.99 is even closer to 1. 0.99999 is incredibly close to 1. So you can see, if I have 0.9 repeating and I have infinitely many 9s, I am as close to 1 as I can get. If I am as close to 1 as I can get, I must be at 1. Because there is no difference between me and 1. If there was a difference, then I don't have infinitely many 9s, which clearly I do. If you get infinitely close to a number, you are at that number. Number 3, infinity is not a number. You kind of already know this, but by definition, you can't count to it, right? And number 2, what even is infinity? Is infinity the number of integers that exist? -1, -2, etc., 0, 1, 2, etc. Or is it the number of real numbers that exist? 0, 0.1, 0.01, 0.001, 0. Right? There's a bunch of infinitely many quantities out there that you can't really just relate to one another. You can't just directly compare those two. All this to say, infinity is not a number. We are going to say, in some cases here, that x, for example, is approaching infinity. Here's why we get away with that. We're not actually saying we're going to plug in infinity for x. We're just saying x is increasing without bound. It's just going to keep going. It's going to keep getting bigger. It's going to keep getting bigger. And then we'll see what happens as you plug in bigger and bigger x's. But that's the idea. That's when we can get away with infinity. It's just saying bigger and bigger and bigger is really all that's meant to represent. Okay, let's get into it. First of all, quick review on what a limit is. You know what? Let's go back to x minus 2 over x minus 2 for a second, because I feel like that's a nice example to illustrate why we care about limits. So when you have a hole like this, obviously you cannot just plug in and get the y value of the hole, because that's what makes it a hole. You can't plug in. So if I wanted to say, well, what's the, where is that hole? Obviously it's at x equals 2, but what is the y value that hole occurs at? What I could do is I could get really close to 2. I could plug in x equals 1, and then x equals 1.5, and I can plug in x equals 1.75 and 1.99999, right? And all of those guys are going to be well defined. All of those guys are going to lead me right up to the y value of that hole. And similarly, on the other side, you could go 3, 2.5, 2.1, 2.00, 0.1, etc. So the idea is, a limit is basically plugging in when you can't. Instead of plugging in, we're going to just start over here where you can plug in and get really, really close to where you can't plug in. And then that'll give me a pretty good idea of what's going on where I can't plug in. What is the y value that's missing from this graph? So if I wanted to formalize this, I would say, well, the limit of x minus 2 over x minus 2 as x approaches 2, that's 1. That's 1. And there is some slight nuance here. Because what if I have a graph that looks like, what if I have a graph that looks like that? Here we have, of course, what we know as a vertical asymptote. We'll talk more about that, but what's the limit there? Well, we kind of have an issue, right? Because as we're coming from this side, y is getting bigger and bigger and bigger, and as we're coming from this side, y is getting bigger, but it's getting more negative. So how am I going to assign a value to that limit, right? Because it depends on how you approach it. That's going to change the answer. So what we do is we say, basically, this answer, they don't agree with each other, so there's really no way of assigning a value to just approaching. So we're going to say that limit is undefined. Limits are undefined when how you approach a certain value changes what the limit is. So then asymptotes. Poles and vertical asymptotes in a way are kind of related because, a vertical asymptote occurs at a y value, or rather at an x value that you can't plug in, right? Like this guy right here. This is, as we shall see, this is x equals 1 that you cannot plug in. And then poles also occur, of course, where you can't plug in. That's at -1, as we shall see. So how do we tell the difference between those guys? Well, I think I've already hinted at it. What we're going to do is we're going to say, where can I not plug in? And then, does it seem feasible that I should be able to plug in there? As you can see with a hole, it seems feasible that I can assign a y value to the hole even though it's not actually there. Whereas with an asymptote, good luck, right? We're going way down on this side, way up on this side. There's really no coherent y value that that's hinting at. First of all, this is the real trick. Notice that or that x plus 1 over x squared minus 1, that's the same as x plus 1 times x minus 1. And then on the top we have x plus 1. So if we're looking for a hole or a vertical asymptote, obviously we're looking for an x value that's gonna make the function crap out in some way. Here, what that's going to look like, because we're dealing with rational functions, right? When we're talking about asymptotes and things, we're almost always talking about rational functions. Really, the only way that we can make this function crap out is if we divide by 0. And there's two ways of making the bottom 0 here, right? We could plug in -1, or you could plug in x equals 1. So that's two x values to check that maybe there's an asymptote there, or maybe there's a hole there. So what I'm going to do here is I'm going to say I can't actually plug in x equals -1, but what I could do is get really, really close to x equals -1 and see what happens. So let's do that. The limit as x approaches -1. All right, now notice, because this is a limit, we're not actually plugging in -1. So you know what we can do now. Because -1 is not a problem, because that's a value we're never going to hit, we can actually just cancel these guys, because we're not actually hitting -1. So then how am I going to evaluate this limit? Well, the only real issue that we're going to see with this function might be at x equals +1. Other than that, we should expect this function to be continuous. We should expect it to not just jump suddenly. So if we're approaching -1 and the function is continuous around that -1, then whatever we get is going to be super, 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 super close to if I had just plugged in -1. In fact, it's going to be so close that it's infinitely close and it's going to equal if I had just plugged in. So because of the continuity of this function, might as well just plug in. -1/2 is where you're going to get there. All right? So because I can actually assign a y value there, we're going to say by definition, x equals -1 must have a hole. So then what about our other guy? Let's see if that's an asymptote or a hole. Same idea. Can't actually plug in 1, of course, but I could approach 1. Now we're approaching 1, so we're not super worried about what happens at -1. So might as well cancel those out because -1 is not a concern for us. And we're going to get a limit as we approach 1 of 1 over x minus 1. That's still an issue, right? I can't just plug in. Anyway, if I did plug in, I would get undefined. So we're going to have to actually approach this time. Let's say I plug in something slightly bigger than 1. It's going to be really, really close to 1, and it's going to get closer and closer to 1 as we take this limit. But let's plug in 1.1, for example. So then on the bottom, 1.1 minus 1 is just 1, and I get 10 when all is said and done. And then of course I plug in 1.01 and I get 100. I plug in 1.001 and I get 1,000. So clearly, if we're coming from slightly bigger and we're approaching 1, we're getting really, really big. On the other side, if I plug in slightly less than 1, then let's say it's 0.9. then I get negative 0.1 on the bottom, I get negative 10 overall. If I plug in 0.99, I get negative 100, 0.999, negative 1,000. If my x is approaching 1 from the slightly bigger side, I'm getting really big numbers. If my x is approaching 1 from the slightly smaller side, I'm getting really, really negative big numbers. I'm approaching two different things depending on how I approach. By definition, this limit is not a function. So there's your vertical asymptote at x equals 1. So let's check this guy for a horizontal asymptote. Horizontal asymptote, the way we define that is it is some y value that we can get as close to as we want, arbitrarily close to that guy, but we're never going to hit it. Well, look here. If we get arbitrarily close to a number, technically we do hit it, right? So the only way for us to get as close as we want to it without hitting that y value is if whatever x value we actually hit at is not an x value we can actually plug in. Not an x value we can actually reach, that is. What's an x value we can never actually reach? Infinity. So really what it boils down to with a horizontal asymptote is what are we approaching as we go to negative or positive infinity? Let's say I plug in 100 here. On the top I'm going to get 101. On the bottom I'm going to get, what is that, 10,000 minus 1. So clearly I have a way bigger number on the bottom. Of course, you divide a number by a way bigger number, you get something very, very small. Keep plugging in bigger and bigger numbers, maybe 10 billion. I get something way bigger than 10 billion on the bottom, right? In fact, I get something about on the order of 10 billion squared. The bottom is way, way, way bigger than the top. We're approaching a very, very small value. So as you can see, if I keep plugging in, I'm getting smaller and smaller and smaller and smaller and smaller, and I'm approaching 0. What happens if I go the other way? Is there a horizontal asymptote that way? Well, it's the exact same idea. One slight change. Plug in a really, really big negative number. I don't care what it is. What happens? Well, the bottom is once again way bigger than the top. Also, negative number squared is positive. So something really big and positive on the bottom, something really big but not as big, and negative on the top. So now we're getting this negative number, but that negative number is very, very small because the bottom is so much larger. So as we plug in bigger and bigger numbers, we get numbers closer and closer to 0, so clearly we are approaching 0. What about a slant asymptote? Let's move over to this guy. So this guy is clearly going to approach infinity if I plug in bigger and bigger positive numbers. But a slant asymptote, the way that works is we can ascribe a certain pattern to how it approaches infinity. 2x squared minus 3x plus 1. If I divide that by x minus 2, I'm going to get 2x plus 1 times x minus 2, and then there's that remainder of 3. If I want to see what happens if I plug in bigger and bigger numbers, I'm not concerned about the fact that the function is not defined at x equals 2, because I'm way over here at like 10 billion. So what I'm going to do is I'm going to say that's equal to 2x plus 1 plus 3 over x minus 2 away from x equals 2. In which case you can then see that I plug in bigger and bigger numbers, I'm dividing by something gigantic here. It's very, very close to 0. So as I plug in bigger and bigger numbers for x, I'm approaching just whatever 2x plus 1 is, because this is going to get so negligibly small. As x approaches infinity, the function approaches 2x plus 1. That's our slant asymptote. Fun exercise to try if you're feeling like you might need a little more practice with this, but you're starting to get it, is that you could try plugging in x equals negative infinity and show that it still approaches 2x plus 1. You could also show that x minus 2 is not, or that x equals 2 is an asymptote rather than a whole, because as you approach x equals 2, you're not going to get the same thing depending on how you approach it. I don't think it made it into the edit, but the bell just rang, so I should probably go. But yeah, that's the gist of it. mualphatheta.com. Bye.